Today, I want to talk about the molecular barcode. At first it was my master thesis, and then I continued working on it. And at first I want to motivate this, but basically you all know about this. I really need to emphasize how important fair data is. But we can imagine, like we do it also in our group, we are computational chemists, theoretical chemists, and we collaborate with the experimental chemist, and we may want to store our data in databases. And so our data comes from different sources. We might have a computational chemist who does some quantum chemical calculations. So he stores maybe his Cartesian coordinates of a molecule in a database. We might have an experimental chemist with the crystal structure, or another experimental chemist who stores his structure information maybe in a ChemDraw in a ChemDraw file. The question now, of course, is how to remove duplicates, because, okay, here we see all three database entries are referring to the same molecule, so it should be only one database entry at the end, because data storage increases, and also if you want to update the data later, then it might be difficult to do that. And of course, you know the answer to it. We use molecular identifiers for it, for removing duplicates, because then we'd see, okay, this is the same molecule all the time, and then we can remove duplicates. So now, of course, the question might come up, why we are working the different one? Why for us, at least for us computational chemists, we have some problems with the INCHI so far. One reason is that most of the time we don't have an SDF file, or like the connection tile format. We usually only work with Cartesian coordinates, and we only have Cartesian coordinates. And this information here, like in the bond block, that's not that trivial to get, right? Because, okay, what is a bond? First of all, that can be a philosophical question in the end, or where do bond orders come from, right? They might differ based on the level of theory you use. This is not a trivial question. And what we see, for example, if we have only an XYZ file, as it is the standard in theoretical chemistry, if I use different XYZ to SCF file converter, in the end, I might get a different INCHI. So, and this is a bit problematic for us, because if we want to combine our data with other computational groups, then we might find not all duplicates in the end. So for us, it was important to get an identifier that supports naturally XYZ files. The other thing is, because like what we do in our theoretical studies is that we deal a lot with photocatalysis. And for photocatalysis, we deal a lot with molecules that have axial chirality, planar chirality, so global order chirality, higher order chirality. So, for example, this year is a catalyst from a cooperation of our group, from my colleague Pitt Steinbach, and he worked on this photocatalysis, and there is some sort of axial chirality, and INCHI is the same for both enantiomers. The same thing for metal complexes. We deal with a lot of homogeneous catalysis, and we want to store our data also for axial, for molecules with axial chirality, and also metal complexes. And that was basically the reason why I tried to work on something different. And that's enough for the motivation. And this leads me then to the molecular barcode I'm working on. And we start basically very, very simple. This is really standard in a sense, because, okay, at first we might want to describe connectivity. So where is the bond between which atoms is the bond? And this can be done, of course, by molecular graphs. And typically, molecular graphs can be described by a so-called adjacency matrix. And you know this maybe also from theoretical chemistry, like a Hückel matrix is nothing else but an adjacency matrix. And what we do is we use an extended one. What does extended mean? We have some values on the diagonal, which encode our atomic information. And then we have on the off diagonal of this matrix some bonding information. Every time there is a bond, it's just like a measure based on covalent radii. We have a mean value. So we see, okay, here we have element information, and here we have the bond information. So with that, of course, one could already describe constitutional isomers, but what about permutation invariance, right? Because we could change columns, interchange columns or rows, and we get a different matrix, and then we have a different identifier. This would be good. So what we do is to just calculate the spectrum. So just some math. We calculate the eigenvalues of a matrix, and we sort them by order. So those are basically the same molecule, but a different order. So a different adjacency matrix. Those are the eigenvalues of that matrix. And per definition, that is a mathematical fact, a definition. This is always permutation invariant. So we can change columns on rows. It doesn't really matter. So we can have a quick check if this really works. I just show you here different constitutional isomers of C9H8O4. And you can really see, I just highlighted the first eigenvalue here. Those are really different. And by the way, we only use integer values of the eigenvalues because that is already enough. The other thing is now, the global order or higher order chirality, right? Axial chirality, planar chirality. So again, this molecule here, and we want to describe this as well with our identifier. And what we can do is to go through literature and we borrow some theory of optical activity. And I don't want to go into the derivation or anything, but this is based on the optical activity, like ECD spectra. And with ECD spectra, you can differentiate between two enantiomers no matter where the chirality is coming from. This is a very old paper. This is not an index from us, but a paper from 1995. I think it was never really used so far as I know. But it works for us because we can see for those two enantiomers, we get a different value in the end, which is pretty cool. So we can now describe axial chirality. However, this is again from our cooperation with some experimental scientists, and there we did we calculated the ECD spectra, and we see that the ECD spectra depend on the conformer. So here we have the same enantiomer, but a different conformer, and we see that the values of the index change based on the conformer, and which makes totally sense because also for a real ECD spectrum, it depends on the conformer. Of course, our identifier should not depend on the conformer. We want to be conformer independent because conformer for us chemists is just the same molecule in the end. So what we use there is a force field, basically. So this is just an really specialized force field that I implemented, just harmonic terms in the end. What we do is, for example, here, this ring structure, we can have different conformers for this ring structure here, but we just make it flat. The same here, we have another conformer, we also make it flat. So those two are different conformers, but in the end, with that force field, we have the same structure. You could of course say this is really not a physical structure, right? We make this ring flat here. This doesn't make any sense, but we want to describe chirality here, and we still have the same information. We know we have here a plane, and this group here is above that plane, and this information is not really lost. One problem is, of course, that, for example, here we have a single bond, right? We can freely rotate that single bond. This is quite hard to get a single minimum in the end because if you have different groups here, you want to always have the same minimum. This is a bit complicated, but what we just do is we leverage molecular stiffness because all the time we want to describe something. We have some sort of constraint in our system. So for EZ isomerisms, cis-trans isomerisms, here we have something like a ring, or for the axial chirality here, this plane. Every time the molecule is very, very stiff. So what we just do here, we have a really flexible ring system. We just cut it and we create fragments, and those fragments are defined by some sort of yeah, there's stiffness. So if for rings, we say it's a fragment. For double bonds, we say a fragment. We can also have combined fragments. So we cut it and then idealize it, and then we can describe this structure here with our index. So now we can describe enantiomerism, chirality. So for example, here, those are the fragments from the slide before. We see there's a different orientation of the oxygen groups here. So we can really see, okay, those two are enantiomers. Of course, we need to also describe diastereomers. For this, we just, yeah, this is really semi-empiric stuff, I would say. It's yeah, based some sort of a repulsion energy. Those p-values here, you can imagine them as pseudo charges. I don't want to go into it, but you could say, okay, as a freshman in organic chemistry, we learn prioritizing groups, right, for the carbon atom. And this is just the same concept extended through the whole molecule. We do it so we can really see, okay, this atom here is unique in the whole molecule or not. And yeah, with that, we can then describe, we have another index to describe diastereomerism. And this leads me then to the final representation. What we not also do for the indices, we also put them in matrices and we calculate the eigenvalues, and you can really see it here. And this is then the final barcode. So at first we have some version, maybe there might be changes in the future, and we really want to check them, that we really compare the same barcode in the end, the same version of the barcode. This blue one here is then the connectivity I showed you before. The green one is also the connectivity, but in this case without hydrogen. So in the end, we can differentiate between tautomers, right? So for tautomers, the blue one, the blue part would be different, but for the green one, it's the same. And in the end, we would know, okay, this is a tautomer. Here we have then the eigenvalues for diastereomers, and here we have the eigenvalues for enantiomers. And yes, this just, yeah, now I want to show you a few examples where we applied it, we ran some tests. And then first, of course, we wanted to see, okay, basic organic chemistry, 2-electron, 2 center bonds, central chirality, and so on and so forth. And yeah, I retrieved a data set from PubChem, 36,000 molecules, only XYZ format, so no SDF files, and we tried to run them. And we calculated canonical smiles in Inchi as well, and we see roughly we have the same number of duplicates found. There are some changes. I looked through all of them. I don't want to go into it too much, but most of them it's smaller bugs, nothing really severe. So for normal organic chemistry, if I may say so, then every 3 identifiers are quite similar. Of course, like, yeah, this is only one example I wanted to bring. So here we have a different barcode in the end. Inchi is the same. There is a difference between the hydrogen position. So here's, you can say, okay, we have some sort of tautomerism, right? But also the barcode calculates here a bond order of 2. So this is stiff for the barcode. So we have a different EZ. Yeah, this is maybe something for discussion. But yeah, most importantly, here we have some tautomerism. And yeah, I checked it, like if this is really a double bond that is fixed in an MD simulation, it appears to be so. Okay, then just some smaller examples, some molecules are brought to use. So we have some delta lambda complex here and we see, okay, here we have a -1, there's a +1. So we can say, okay, we have different enantiomers here. Inchi is the same for transplatin and cisplatin. No, it's not chirality, but like this repulsion term here, this pseudo repulsion here is different. Yeah, another example here, chiral C74. We see, okay, we have one enantiomer and the others. In this case, this is smiles, and for archival Buckminster fullerene, we see it's also like a 0 here. So we know it's archival in the end. And yes, here's another example for metal complex. Here the position here with chloride, and here's the CN group. Those are on the other side. So the barcode here is again with that repulsion term. We say it's a different molecule, and Inchi here is the same. All right, so this brings me already to my conclusion. So I showed you this molecular identifier, which is now based on a fragmentary approach. So we calculate fragments instead of like really have an atomic description like in Smiles and Inchi. We do that to really include global chirality, or to describe global chirality. This is really optimized to receive Cartesian coordinates only, and we support in general inorganic and organic molecules. One last sentence maybe for inorganic molecules. There might be sometimes still a problem with finding bonds in a metal complex, right? This is really not a trivial question if there's a bond or not, if this is also if this system is flexible or not. This is really something for the future, but for where the bonding is quite clear in the metal complex, there it works. And this here is a Python package, so in a couple of next weeks, one can install it with pip. So it's written in Python. The heavy part is written in Fortran, and I think that is it. Just saying thank you for Christoph for the nice, really good supervising. Pitch Steinbach, because I borrowed a slide from him. Of course, all the other colleagues I want to thank, and some funding, and of course, again, NFDI for Camp for inviting us. We are really glad that we can be here and present this work to you. Thank you very much.